Today we have Bill Willems, who is one of the lead scientists working on LIGO. He's going to talk.
What's his name? I'm sorry, what's your name?
Phil Willems.
Let's write it down. Yeah. And you know, I'm not able to judge experimenters, but Brzezinski says he's superb. And so Brzezinski says that about very few people. So Phil's going to tell us about various forms of thermal noise.
Okay, I won't tell him you said that. All right. So yes, I will talk to you today about thermal noise, and I want to apologize in advance because, well, the thermodynamics of thermal noise and the mechanical underpinnings of it are fairly clean and elegant theory. The application of this theory to an actual working gravitational wave detector involves a lot of disparate fields of material science and electrodynamics, where the important parameters, the important quantities that you want to know or measure are very difficult to calculate and not very well related to one another. So the latter part of this talk is going to end up being sort of a grab bag of different types of mechanisms by which thermal noise can enter an experiment. So what is thermal noise then? Any object which is at a non-zero temperature is going to have heat energy, and this energy is manifested basically as a mechanical motion of its constituent parts with respect to one another. The temperature is only an average property of a material. The energies of any, say, individual atom in a gas or in a solid body are going to be distributed statistically with a distribution which is determined by this average temperature. For example, in an ideal gas,
just for, if you're interested in, I don't know, are you filling all the boards?
Probably, yeah.
Okay, so you want to use the top board first.
Pull the top board down.
Ah, okay, this one doesn't go up. Okay.
Rooms like this for 5.
It's been about 8 years since I attended a lecture in here. For an ideal gas, the probability of excitation of the occupation of a certain state E is given by a Boltzmann distribution. Where Z is the partition function. Well, not really infinity, but for as many states as there are. Where I labels the state. And so you can see right away, simply by looking at the Boltzmann distribution, that for a given temperature, there's any range of a number of energies that can be possessed by an atom, or a degree of freedom, more specifically, in the system. And thus, if you're going to be sensitive to the motions of some subset of, sorry, you're going to be making an experiment which is sensitive to some subset of the constituent parts of the system, then you're going to be observing these fluctuations. The traditional example of this is Brownian motion, which was first observed by Robert Brown using dust grains in a microscope in about 1828, and first explained by Albert Einstein in 1906. And to understand Brownian motion, I find the Langevin approach to be the most useful and generalizable way of thinking about it. You simply ask, what is the equation of motion for this dust grain in the system? Well, it's got its inertial term, the mass times the acceleration, is equal to some velocity-dependent friction, to which you add some fluctuating force. Now, the friction is due to the individual atoms in the liquid in which the dust grain is floating. The fluctuation force is also due to the random motion, uncorrelated motion of these atoms. And in the Langevin approach, what we basically say is there's a macroscopic motion which we can characterize by its macroscopic quantity, and a microscopic stochastic motion, and these are separable. And this is perhaps an odd assumption to make at the outset, but it gives you results that are accurate and gives you a very useful way of thinking about the problem. To find out how Brownian motion, what the size of the Brownian motion is, a good way to characterize it is just the root mean squared fluctuation in the root mean squared position of the atom. You know, we will take an average quantity rather than trying to explain in microscopic detail the precise path taken by the atom. We can do that fairly easily. We multiply this equation by x. And then use the fact that that x, the second derivative of x times x, is equal to the second derivative of x squared minus the square of the velocity, just the chain rule. Applying this sort of reasoning throughout leads you to the following equation. Sorry, I forgot a 2 here. And I want to make it clear that I'm not taking the second derivative of x, but the derivative of x squared. Okay, now rather than talk about the motion of a single atom, we take an ensemble of these atoms and ask what the average motion of these is. So we speak about average quantities here, and there will be an average of this fluctuating force. Now, by the equipartition theorem, we can immediately identify what this is. This is the average mass times velocity squared. This has to be equal to kVt. Now, what can we say about this term right here? Well, x is essentially a random variable. It's fluctuating. The force on the atom is also fluctuating with time. And we'll make the assumption now, which could be proved, but is fairly detailed and not illuminating, that the average of this fluctuating force over the position of the atom is 0. That is to say, due to this random motion, all these atoms aren't drifting off to one side or drifting off to the other side. Well, the fluctuating force has now dropped out of the problem. All of the thermal arguments are in this term. This leaves us with the following fairly simple equation. And we can solve this equation, which is now simply just a velocity damping classical equation. Sorry, it's an ordinary differential equation for the root mean value of x squared. And we find that excuse me. So the motion of this atom is going to decay from some initial value and reach some velocity of this quantity is going to reach some steady state value given by this, which means that the root mean squared position is going to tend to the value I'm sorry, did I say C here? This is B. Yes?
A couple of questions. So first, this is a spatial average, is that right?
This is an average over an ensemble of dust grains.
Oh, okay.
So you want times time.
Yes, I'm sorry.
So there are a couple of things that are sort of notational.
Yes.
Slides at the end I want to make sure I understand. So that since it's not ensemble average, we can take the average inside the derivative.
Yes.
Average of the derivative of the average.
Yes.
And another thing is in the second to last line, I just want to make sure that it is the average of this. We're talking about the mean square, so it's the mean of the square, right? So
Yes. That was just sloppy penmanship on my part. Sorry. I need to be more careful. Yes.
Because those are different.
They are different. The mean is actually 0.
Right. Because, yeah, again, the same reasons as the fluctuations.
Yes. Okay. So this describes the stochastic motion. If you're monitoring the position of this dust particle, you're going to see that it's random. It's going to increase with time, and its root mean squared is given by the heat energy and this damping term, which we can equate to a dissipation. And we can see then that the thermal noise motion of this dust grain is somehow related to the dissipation. Now, this Langevin approach can be easily extended to, for example, a pendulum suspended in this gas. It's a simple harmonic oscillator, so all we need to do is go to our Langevin equation and add a restoring force. Now, if we were to apply this same trick that I used here, again, right here, I can tell you right away that when we take this term and create this term, we'll get kT squared by the equipartition theorem. When we do the same thing here, we'll get a term that's like kx squared averaged over the ensemble. That, too, by the equipartition theorem, is going to be equal to kBt squared. And those two terms will cancel, and you'll get an equation of motion which is just a damped harmonic oscillator, or just a damping term. Everything goes away. It's self-consistent but not very illuminating. What would be more interesting and more useful for our purposes, because we don't care about root mean squared motion, but about the actual spectral density of the motion, because after all, we're trying to look for gravitational waves in some bandwidth. Is to use the spectral density of the force. Now, this force, this fluctuating force, is made up of what? This fluctuating force is a bunch of atoms impinging on the test mass randomly, uncorrelated in time, with little impulses characterized by the momentum transfer upon recoil. So they're basically uncorrelated in time. Therefore, the average of this fluctuating force is going to be equal to 0. The 2-time correlation function of this force is going to be given by a delta function. In other words, this force is only correlated on timescales that are very, very short compared to an atomic collision. And that correlation strength is something like Q. And that Q is the strength of the force. In this case of the Brownian motion in a gas, it's easy to show that Q is equal to this. We can then find the spectral density of this force. Which is just given by the integral, the Fourier transform of this two-time correlation function.
So this is the Wiener-Henstein formula.
This is the Wiener-Henstein theorem.
Which is in the reading that I've given you for that I gave you late last week.
Now we assume the process is stationary, therefore independent of t, so this actually just becomes equal to this. And given this, the fact that the force is equal to this, we can find that the spectral density of the force is simply 2q, independent of frequency. That's white noise. If we wanted to, we could then use a formalism like this to get the spectral density of the position of the mass in this Brownian motion. What we want there is to use the Wiener-Henstein theorem again, but instead of the force, we want the position. Now it's a complicated task to do this. We would take the force at a time tau, equate it to the motion using this equation of motion. Take the force at 0, equate it to this equation of motion. We get terms in here that are proportional to x at tau times x dot, the first derivative of x at tau times x, the second derivative of tau times x, of x at tau times x, and so on and so forth. Solve for all of these different two-time correlation functions in terms of this one and finally get an answer out. And it's a lot of work, but you can get the answer out. But there's a much easier way, and that's to use the fluctuation dissipation theorem. I'm going to give you the answer first, because it's quite simple. The fluctuation dissipation theorem allows you to relate a fluctuating force due to a dissipation mechanism. Here we're taking the spectral density of the force. So let me just say that. Where Z is an impedance. So the spectral density of the force is given by the thermal energy in the system, or in the reservoir, times the real part of some dissipation Z, some complex impedance. This can be a mechanical impedance, it can be an electrical impedance, it can be any sort of impedance. The way we define the impedance is that the impedance is given by the ratio of the force applied to the system to the velocity of that system in response to that force. This can also be expressed in terms of the spectral density of the response. That also has a very simple form. That's just the heat energy times the complex admittance of the system, or Y, is equal to z to the negative 1. And again, only the real part of the admittance of the system, what we would call the dissipation or the friction. This is a theorem of surprising generality within physics. It can be used to explain the Brownian motion of a dust grain in water. It can be used to explain the fluctuating voltage across a resistor, which is at some finite temperature T. It can be used to explain spontaneous atoms, the spontaneous emission of excited atoms into the vacuum. It's a very powerful tool, a very general tool. What I'm going to do now is show you how it is derived. Do you think we have time for that, Kip?
Well, you know what you want to cover.
Okay.
So I will give them some reading that has a derivation. So
Okay.
You can, but it'll presumably be a different derivation than you get. So,
I'm going to give them the Callan derivation. The Callan derivation.
yeah, I don't know. It's probably a different derivation. It's my own derivation.
Okay.
And, pardon? Yeah. So go ahead and do it.
Okay.
Cover the ground you want to cover.
Okay. Well, given that I have only an hour and a half and it's fairly long, I think, and you're going to give it to them as reading, I'm going to skip it. This is provable. You'll be reading about how it's derived. But simply assume the result.
I'll give you a fairly short derivation, and then I'll give you the reference to the Callan paper, which is much deeper, where you can see a more sophisticated and more general derivation.
Okay. I would like this to derive this for you, but it would take more time than I think we have today. We can use this formula, or rather this formula, for the damped pendulum to determine what the spectral density of the position of the pendulum is. If we work in Fourier space and apply some sinusoidally varying force to the pendulum, we can immediately, if we assume that the motion is also sinusoidal, get the following answer for the motion of the system. Which is quite simple. We plug this into here. The x in here just comes out with an e to the I omega t. We take a first derivative. That brings out an I omega in front. So there's 1 power of omega. The second derivative takes 2 powers of omega in front. So m omega squared.
You want to get rid of one of the f moles.
You're right. The velocity is just equal to the first derivative of that with respect to time. Do a little bit of algebra to separate the real and complex parts and put them in the derivative.
We're just solving
spring?
We're just solving the force spring. You know the answer to that. That's right. And finally, you can find that the admittance of the system, which is equal to the velocity over the applied force, is equal to I omega over k minus m omega squared plus IB omega. And the real part of this is equal to so we can take this, plug it into the fluctuation dissipation theorem, and get that the spectral density of the noise is given simply the proof takes just 3 lines, and we've got the spectral density of motion of this pendulum due to thermal noise in the presence of this fluctuating, in the presence of this damping. Very simple, very powerful. The spectrum has the form so if we take the motion, which is basically the square root of this, which has dimensions meters per root hertz. In order to find out how much motion you have in a certain bandwidth, you'd simply integrate this over the bandwidth you need. This is the resonant frequency of this simple harmonic oscillator. For example, the resonant frequency of the pendulum frequency. And the thermal noise is basically flat, well below the pendulum frequency, and falls off inversely with the square of the frequency above. This then is the thermal noise spectrum of a pendulum, which is suspended in some sort of viscous damping, for example, inside atmospheric pressure. And this was easy. Yes.
If you integrate x over the frequency range, would you ever do that?
Pardon? You would integrate x squared over frequency range to get a root mean squared motion over.
Okay.
Yeah.
Okay, so that's why it was square. That's why it's x per root hertz.
Yes.
Because we square it in order to integrate over frequency in order to get the.
Right. This tells you what sort of RMS noise motion you'll be having within some given bandwidth.
Or if you remember, S sub x of omega, when I motivated, came from the theorem that relates the integral of square Fourier transform.
You know, some people call it partial oscillator.
And so this guy is basically the frequency side of Parseval's theorem, integrated over frequency to get the mean square value of the fluctuating quantity x. It's always, that's really the nature of the purpose of the role of the spectral density is primarily just to do those integrals over frequency. See how much mean square fluctuation you have in a given frequency.
How do you get x from between the spectral density? I'm trying to figure out where that plot came from.
Well, this noise is basically the square root of this.
So in this field, people write x of that, and they mean the square root of the spectral density.
Okay, that's
the notation generally used by gravity wave physicists.
Okay.
Yeah, because over here just annoying right back or something.
Yes. Now, the power of the fluctuation dissipation theorem is that it greatly simplifies the thinking that you would otherwise need to do about some thermally agitated system. In the Langevin equation approach, here we have a fairly simple, for example, dynamical system, a damped harmonic oscillator, with a fluctuating force on it. But we begin having to ask questions. What is the nature of this fluctuating force? What is the time scale of its fluctuations? Is it, how correlated over time is it? Where is it within the body of the system? Is it throughout the system or to one side of the system? Where is it forcing the system?
That's a log-log plot too.
This is a log-log plot.
Yeah, I'm sorry.
Sorry about that.
That's a major line too. It's like it's slow. Okay, I'm sorry.
In this approach, all you need to do is, the thermal energy is all here. That's everything you need to know about the heat energy of the system right here. The impedance, or equivalently the admittance, since they're very simply related, tells you everything about the mechanical motion of the system, or the electrical motion of the system if you're worried about some sort of electrical fluctuations, and the nature of the dissipation, the friction in the system, which will inevitably lead to these fluctuations. What this means, experimentally, is that if you want to study thermal noise, you're given two choices, a very easy one, or a fairly easy one, and a fairly hard one. You can measure thermal noise directly, and this can be done, but it's very difficult, because measuring noise, in fact a very faint noise, in the presence of many, many other noise sources is a very daunting effort. Or you can measure dissipation, which is typically much easier. And it gives you a better handle to understand where the noise in the system is coming from and what one might be able to do about it. So in order to understand thermal noise, we need to understand dissipation. For the most part, we'll be talking about mechanical systems and mechanical dissipation, friction. So a very easy and conceptually simple way to mathematically describe dissipation is to work in Fourier space. You do Fourier transforms of your physical quantities and let, the elastic modulus, the Young's modulus, for example, of your system be a complex quantity. The real part of the Young's modulus is what we would typically call the elasticity. The imaginary part of the Young's modulus is what we would typically call, what we call the dissipation. And I'll explain why that is. If you want to know the dissipation in some sort of physical system, it's very easy. Take that system, apply some cyclic stress to it. One cycle. You're going to do some work on that system, given by this simple form. If the amount of work done in a closed loop around the system, after you've gone through some loop in stress-strain space and back to the origin, is non-zero, then the process that you've just done is irreversible. There's some dissipation involved. For a very, very simple system, the response of the system to some force is just given by the force divided by the elastic modulus. And so this interval can have a fairly simple, this integral can have a fairly simple form. Rather than integrate over some closed loop and strain, we'll use the fact that we're going to make the force complex and the response complex. To show that x is equal to and in the limit that the dissipation here is very small, we can do a Taylor series expansion and bring it up to the top here. This is a phase lag now. the response of this system to some applied force at some frequency is itself sinusoidal, but with some phase lag. When you then plug this into your equation to figure out the dissipation, you get some equation of the following form. Let me simplify. Here, basically what we're doing is we're letting dx equal dx dt over dt, and transforming this integral over strain to an integral over time. There we get a velocity. We take the real parts of these quantities because when you're working in Fourier space, it's fine to handle imaginary quantities, but when you start multiplying them together, it's important to use only the real parts. What this gives you is this is equal parts sine and cosine. I'm sorry, because this is a velocity, we have to take this. And there's my omega there. This is equal parts sine and cosine. This is cosine. The integral of cosine times a sine over one period is 0. So we want to take only the sine component of this exponential in the integral. We can see that since the product of cosine times cosine, cosine squared is not non-zero when integrated over a closed loop, that there is going to be some work done on the system if phi is not 0. Therefore, phi is expressing a dissipation, and this is a logical way to express the dissipation of a system. Now, there are many kinds of loss, and the convenience of expressing phi in this way is that we can put all of the frequency dependence of the system, or the frequency dependence of the dissipation, into phi. Now there are basically three kinds of dissipation that we see mostly in nature. This velocity-dependent dissipation is just a phi which is proportional to frequency. And we can call this viscous damping. Most materials exhibit a phi which is basically independent of frequency. In other words, the losses are the same no matter what frequency it resonates at. We call this structural damping. The mirrors of LIGO test masses, the wires that suspend the LIGO test masses, these for some reason all seem to have frequency-independent damping.
Let me just go back and highlight something, Bill.
Yes.
Your definition of E is that if you have a test mass,
yes,
you displace it sinusoidally under the action of some force. And E is the ratio of the force divided by the displacement.
Yes. It's a spring constant or an elastic modulus.
Not necessarily the Young's modulus of the material of which this is made, because there are many other, there's a wire attached to it and other things.
It's a generalized sort of modulus. Any stiffness against an applied force could be this.
So the definition is that it's F over, that E is F over X in frequency space.
Yes. We're taking all masses out of the system, just saying you have a spring, you push on it back and forth. How much energy have you pumped into the spring? How much energy have you dissipated in the spring as a result of going through this closed loop? Okay, viscous damping, the kind you get, for example, due to gas, due to resistance from a gas. Structural damping, which seems to explain physically, describe physically most damping that you see in materials. There's also something that we could call a Debye peak, where the dissipation is given by some strength and is peaked at some frequency, which is given by a characteristic time in the system. This delta just is the strength of it's a constant that you put in there. So this is a damping which for very low frequencies, where omega is very, very small compared to the inverse of this time scale, it's not a very strong damping. For very high frequencies, it's also not a very strong damping, but if you're trying to oscillate it in a certain preferred frequency range, you tend to exaggerate the effect of this damping. This is the most logical form of damping for just about any physical process occurring within materials that we can think of. For example, thermoelastic damping, which I'll tell you about later.
So is the inverse of the frequencies, there are 2 pi's in there, or is that conventional and we don't?
There should be a 2 pi in there. Yes.
2 pi?
No. The peak frequency is given by this.
Okay.
1 over tau.
So, I mean, ordinarily, if you talk about the period, it's 2 pi. It's not really
Yeah.
but it's not really a period, it's just a time scale.
Time scale. Yes. Now, this is just mathematics of dissipation. When you use the fluctuation dissipation theorem to understand what the spectrum of noise is going to be, of noise motion in a system is going to be, what you end up doing is finding the mechanical impedance of the system, the mechanical resonances of the system. It's going to have a certain response which is peaked at some frequencies and not at others. For example, if it's a mass hanging from a wire, it's a pendulum, and it's going to want to move a lot at its pendulum frequency. It won't want to move so much here or there. And then this overall mechanical response will be multiplied by some dissipation function phi, and the frequency dependence of this dissipation is going to tell you what the slope of the thermal noise is in the vicinities away from this resonance. Now, what we're doing in LIGO is trying to build a detector for gravitational waves, which are very faint. In the most interesting frequency band of the detector, around 50 to a few hundred hertz, the thermal noise of the suspension wires and the test mass of the system are going to be limiting factors. They limit the sensitivity of this detector. So what you want to do is try to build this interferometer in such a way that the noise introduced by these components is as small as possible. And the way you can do this is there's 2 approaches that you can use. One is just to reduce or eliminate the sources of damping wherever you find them. The other is to design the mechanical system so that you can push the thermal noise, for example, this thermal noise, into some uninteresting frequency. For example, if you're looking for gravitational waves here, this pendulum thermal noise is not a big deal. If we're looking for gravitational waves here, it's a very big problem. We would want to design the detector so that this peak is perhaps over here. So let's go through a list of the different forms of dissipation that can happen in an actual gravitational wave interferometer and see how they contribute to the thermal noise. To first order, the mirror is simply a mass hanging from a pendulum. The laser beam interrogates its position here. This pendulum is surrounded by a dilute gas. And these gas atoms reflect off the mass every once in a while. Therefore, it must exhibit Brownian motion. And it turns out that for LIGO, because the gas is dilute, the damping is not precisely described by, well, because this gas is dilute, it has a velocity dependence which is characterized by viscous damping. It's easy to show this simply by taking the Maxwell distribution of gas atoms on one side and asking how much energy they impart to the mass or take away from the mass if the mass is swinging this way, and compare that to the Maxwell distribution of atoms hitting it from this direction and how much energy they take away from the mass. What you find is that if the mass is moving in this direction, these gas atoms are going to carry away a bit more energy than these gas atoms are going to add to it. And so you see a damping force. It turns out that the dissipation that applies in this case is given by the gas density times the mass of a gas atom times the thermal energy over some characteristic dimension of the mass times some characteristic scale factor, which tells you something about its shape and how it interacts with these gas atoms, times the density of the mass times the frequency of the pendulum.
Sorry, H was the length of the...
H is a characteristic scale of the system.
C is...
C is a scale, is basically a scale factor of order unity.
So I could absorb C into H if I wanted.
You could absorb C into H if you wanted. Okay.